mass 2 divided by mass 1 plus mass 2 is less than 1. Therefore, my acceleration is less than the acceleration due to gravity. If, for some reason, you get an acceleration greater than the acceleration due to gravity, on a problem like this, something that's a red flag. Now, I'm not saying you can't get an acceleration greater, but it's something that you might want to go, wait a second, is that possible? That it's going to accelerate as if faster or at a greater rate than free fall?
You have to look at your other factors, no?
Yeah. And in this case, it would be something's wrong. So if we stick in numbers, why don't we make this 20 kilograms and this 5 kilograms? And let's just make the math easier. We're not on Earth. We're on some strange planet where the acceleration due to gravity is 10 meters per second squared.
Oh, we love that.
And so my acceleration, therefore, is 5 times 10 divided by 20 plus 5. So 50 over 25, or 2 meters per second squared. Questions before we do away with the frictionless part?
Well, that's right. We're on Jack's version of this. Okay. Let's do this frictionless part.
Now, if we stick with the gravity is 10 meters per second, could we just go back to the first equation and just do, like, well, we would do M1, so the 20 kilograms times 10 would be friction? Because that's the equation. For M, just M1 times acceleration.
Oh. If we have friction in there, then we got an extra term here. We need another equation to resolve it. All right, so let's resolve it. Let's officially put that other S down. All right, so that was 2 meters per second squared, so let's put that over here in case I forget. So if U equals 0, A equals 2 meters per second squared. If we add friction, I would expect, well, what would you expect? If I add friction, would you expect the acceleration to increase or decrease?
Decrease.
I heard decrease very loudly right here. I don't know if anyone said increase.
I said decrease.
I'm assuming everyone shouted out decrease, and I'm just going F. So friction, I got two surfaces rubbing against each other. If I take this situation right here and I just look at a detail right here, so box 1, it's not flat if you get down to the microscopic level. And the table, same, they've got a lid on it. So, if you think about it in this terms, then the type surface clearly makes a difference. You know, how jagged is it at the microscopic level? Well, you can get some sense just by feeling how rough it is, but how rough the surface is matters. And one other thing matters. First off, let's just sort of address weight. It does not matter about the weight, not directly. The weight of the object does not matter. And so here's sort of a quick thought on that. I have an object here, it has a certain weight. Let me just stay off camera. I'm going to push on it. Why did it stop?
Because of friction.
Yeah, friction's acting on it. All right, same object. I'm going to try to give it the same push, obviously. There's some limitations there. I'm going to push again. Did it go as far?
No.
All right, there was greater friction. Did the weight of the notebook change?
No.
So weight did not affect it. What did change when I put those other objects on top of it?
The forces on top, like pushing it down towards the table. Like, not towards the table. Causing more friction.
Good normal.
So what was,
Causing more friction.
okay, so what force?
Greater normal force?
Yeah, it's greater normal force. So if you picture that you got these two surfaces like this, and then with greater normal force, they get jammed together more, so it's a lot harder to move it. So it depends upon the type of surfaces, and it depends upon the normal force. How tightly are they being jammed towards each other? How tightly or how much is one trying to force its way through the other? The surfaces depends upon the coefficient. And I'm going to put up the three that you might run across. Obviously, one of them doesn't have a subscript. Coefficient of static friction. Kinetic friction. Or friction. Now, if I've separated this into static and kinetic, what is this generic here? It depends on what you believe is actually going on. In order to find the coefficient of static friction, and the math behind this we'll get to at some point, I can find this coefficient of static friction between this box and the aluminum, so cardboard and aluminum, or painted cardboard and aluminum, and I can just lift it up. At some point it's going to start to slide. If I know what that angle is, I can calculate the static friction. I can make it steeper, and I can figure out what the acceleration of that object is, and from that I can calculate the kinetic coefficient of friction, or coefficient of kinetic friction. In essence, that's how it's found in industry. That's a simplified version of it, but the principle's the same. Jack?
For the kinetic, is it just specific to that angle? Or
No.
is it just constant?
It's specific to those surfaces. As long as the surfaces stay the same, the coefficient will stay the same. Now, in this model right here, U sub k is less than U sub s. Now, mu sub s tells us basically a breaking point. If I push against this cable, it is not moving. It's not sliding. Static friction is keeping it in place. I push harder, the static friction will build. Static friction is going to match me. It's going to keep matching me until I hit a breaking point, at which point it will start to move. So if I look at the friction and the applied force, F subscript applied, static friction is going to match the applied force until you get to that breaking point. So this would be maximum static. At that point, suddenly it's into kinetic. It's going to drop down, and the kinetic friction is relatively constant. So this would be Fk. Now, when you try to experimentally find these two values, there seem to be very large error bars. In other words, you get a smattering of data, and there's a range of acceptable values, and there's overlap. This is one claim. If there's overlap, depends on how much overlap there is, but if there's overlap in my two ranges, there's statistically no real difference between the two. That camp says the only reason because of experimental error, not that there's a mistake, the experimental error would just be things inherent in the experiment. You can't tell the difference between the two. They would claim that U sub s is the same as mu sub k, and so why bother with a subscript? And in that model, if we look at the applied force and the friction, static's gonna match, it's gonna hit that breaking point, at which point you get that. Now to me, I look at those two graphs and I'm saying there's very clearly a difference between these two. How come they don't know? My opinion is because they don't care. Friction is primarily an engineering issue. It is not a physics issue. Because of friction, because physicists, for instance, in my dissertation, we were dealing with tiny particles. Friction really doesn't make any sense when you're dealing with subatomic particles. Engineers have something that works. It has worked for several hundred years. They are very practical people as a general rule. Why bother coming up with something new?
It broke, no, fix it.
That's right. There is a group at NC State and a couple other places that are actually trying to see if they can come up with something more sophisticated on friction, but I suspect the textbooks really, the biggest textbooks will do is they'll go from here to here. At this point, I've seen this, we had the 251 textbook, the previous 251 textbook had a page talking about this, but use this. I suspect it will change in Europe before it changes in the US. Tradition, physics textbooks tend to change more rapidly in Europe than they do in the US. Your textbook uses this model. So, in a problem like this, so the formulas, well, since that's constant right there, my kinetic friction equals the coefficient of kinetic friction times the normal force. The static friction, the maximum is when it's equal to u_sy, but the static friction is always going to be whatever it is to keep it from sliding until it hits that breaking point, and so it's going to be less than or equal to us times y. Those are the two friction formulas. And then over here, it would just be that friction is less than or equal to u_y. That's the cycle.
We're not using that, we're using those.
Yeah, we're using these. If you look up coefficient, if you type in coefficient of friction and you get a table on the internet, it should give you two surfaces, mu_s and mu_k, because it is dependent upon both surfaces. Oh, one other thing on friction, there are two things going on here with friction. One, if you think about sort of like puzzle pieces or interlocking pieces, there is that certain, a normal force preventing it as the pieces sort of rub against each other. But also, as you get the two surfaces closer to each other, there's an attractive force between the molecules on the surface. And so there's an attraction going on as well. So those are the two things involved. All right, so so let's give it, I gave the mass there, let's make mu_s equal to 0.3 and mu_k equal to 0.2.
Or are we just making those up for this?
Yeah, for this problem. It is dependent, it is possible for mu to be bigger than 1, but probably usually not. That would be rare. Rubber on asphalt, I think, is 0.7, somewhere around there, just to give you some sense. So when we do substitution, so let's get rid of some of this stuff. It's the last of it. Oh, actually. I don't want that either. All right, so now we have another equation. This now goes away, and apparently so does the yellow. Try that again. that goes away, and this becomes tension minus, but which formula do we use? If this thing is starting at rest, we have to figure out, is it going to move or not? If it is going to move, then we would have to use kinetic. If it's not going to move, we have to use static. But first we have to figure out, is it going to move? So you assume maximum static. So first step, assume maximum static. So mu sy is equal to m1a. Why? It's the normal force at that where that friction is. We have a value right there, so this becomes tension minus mu s m1g equals m1a. And so my tension is equal to m1a plus mu sub s m1g. And that's what we would plug in here. And so we end up with m2g minus mu s m1g equals m1 plus m2 times a. And as I'm just throwing in an extra force that's trying to retard the motion. So a is equal to m2g minus mu s m1g over m1 plus m2. So the only difference between it is this extra term right here. If you plug in numbers at the very beginning, you are most likely going to be starting from scratch again in terms of the equations and so forth. If you don't start with the equations, don't start with numbers and just stick with letters, you're just tweaking what you already have. And so it's up to you at the moment that you have to do it, at what point you put numbers in.
It should be the same as the other A as well?
No, we should be getting a different answer.
Different answer.
We should be getting something smaller than 2. All right, so if we plug in, we get 20, wherever I did that math. It's like I erased it. So my acceleration is 50 minus.
It's in the corner.
Yeah, I think you put
Is that the, in the corner of that, is that the one you're looking for?
No, I was looking for the actual work to get to 2 that I think was here. So m2g is 50, mu s m1g is 60, divided by 5 plus 20. So I get negative 10 over 25, which is, well, that's all we really need, but negative. All right. Now we have to interpret it. Math got us, physics got us the equations, math got us to a is equal to negative 0.4, and physics comes back in to figure out what does this mean. Are the boxes going to move if they start at rest?
Yes,
And why do you say that?
because it has a non-zero acceleration.
All right, so if the acceleration is negative 0.4, which way are these boxes going to accelerate? Which way is box 1 going to accelerate?
Downward. No, right, sorry. Right.
But we said A was to the right and we got a negative value. So if this value is correct, we got the 2 masses right here. This is going to accelerate upwards, that will accelerate to the left. So it's going to do that. Justin, you seem skeptical of that. You don't think it's going to happen?
No, I don't.
Therefore, are they going to move?
No.
No.
So a negative here is telling us that if it moves, it's going to accelerate opposite the direction that we had claimed, which doesn't make any physical sense at all. Because once it starts moving in that direction, friction actually acts the opposite way. So therefore, what is the acceleration?
So if it's anything less than 0, it's just 0.
Most likely. I mean, I can come up with situations where that's not the case. But, yeah, if you get a negative, that should be, okay, it's either not moving or I missed something. Or I guess the other choice is, oh, the direction of acceleration is the other way. For instance, if I had a wedge like this and a mass on both sides, and I predict, and I say, let's just assume acceleration is going this way, and we get a negative, that just means, oh, it's going that way instead of this way. If it had been a positive number, at that point, we realize it is moving, and so therefore we use the kinetic, and then we would just pop in, instead of 0.3 here, we pop in 0.2. Again, if you plug in numbers from the very beginning, you have to do a lot more work than if just at the end. But on that note, I will see you tomorrow, because today is Wednesday, I believe. Today is Wednesday, all right. And I have 9